Hi everyone, welcome back to Math 111. This is Scott. Let's get started. The section today is 3.4, Compositions of Functions. Alright, and this is going to come in a couple of installments. The first installment is just combining functions by adding, subtracting, multiplying, or dividing. So these are first what are just called combinations of functions. And we can basically just add, subtract, multiply, divide two functions by doing that to their formulas. We can add, subtract, multiply, or divide two functions. And the notation that we use here would be like this. So we'd say f plus g, or if we want there to be an x involved, f plus g of x. F minus g, or f minus g of x. Fg, or fg of x. And notice on all of these cases, when I want there to be an x involved, I'm putting parentheses around the combination of the two functions in order to indicate that we now have a combination function, and the input here is going to be applying to the whole thing. And then f over g, or f over g of x. And then when it comes to finding the domain of function combinations, the important thing to remember about this is that these were originally two completely separate functions which you mashed together to make a new function. And so if anything was undefined in the original function, then in either of the original functions, then that'll be a problem. And it will be a problem also if it's a value that becomes undefined in the new function. So the domain of function combinations. So check for illegal values at every stage of simplification. And then the overall domain will account for all these forbidden values. All right. So let's just see how this goes. So to start with, let's take as an example something like this. So here's what we're going to find. So find and simplify f. So call this part 1 f plus g, part 2, f minus g, part 3, just f times g, and part 4, f divided by g, and then state the domain of each in interval notation. And then what's going to happen here is we're going to have different pairs of functions f and g. So to start with, the first of our examples, let's say that f of x is equal to x squared minus x. And then let's say that g of x is equal to, let's say, 3 minus x squared. Okay. So here we are going to put them together every which way. We're going to add them, we're going to subtract them, we're going to multiply them, and we're going to divide them. So first off, f plus g. So here, because we are going to be involving an x, how we need to write this is f plus g all of x, and then here what we'll just take is the two formulas for f and for g and just add them together. So this part right here is just going to be f of x, this part right here is just going to be g of x. So f of x is x squared minus x, g of x is going to be 3 minus x squared. Now, if this were any more complicated than it is, if this had been a minus, or if there had been a coefficient here, or if there had been a square here, or something like that, then we would have to worry about these parentheses and distributing and everything. But as is, there's nothing going on here. Now, there are no forbidden values of x here because there are no square roots, there are no divisions, nothing that can cause any of the usual domain issues. So we can just willy-nilly get to simplifying. So we got x squared minus x plus 3 minus x squared. And at this point we do notice a couple of like terms, and not only are they like terms, but they're actually canceling terms. And so we'll have negative x plus 3. So that's what f plus g of x is equal to. Now here, as for the domain, there was never actually any forbidden value. Since there are no square roots and since there is no division, nothing can go wrong here. So the domain is everything. Negative infinity to infinity, all real numbers. There are no forbidden values. Alright, now let's try f minus g. And it's very similar. So again, f minus g, if we want there to be an x, then we have to put parentheses around it and x, and then what we have here is going to be the formula for f and the formula for g, only now they're going to be subtracted from each other. So what that means is we're going to have x squared minus x plus, minus 3 minus x squared, and now we're going to have to distribute the negative. So it's going to be x squared minus x minus 3, and now minus and minus become a plus. So plus x squared. And so these two are like terms, so they'll be combined, and there are no other like terms. So we're going to have 2 copies of x squared minus x and minus 3. So there's that. Again, no forbidden values have appeared at any stage, because we're not doing any division, we're not taking any square roots, so nothing can go wrong. So what that means is the domain, again, is everything. All real numbers, which you can also write as just negative infinity to infinity. All right, now multiplication. Again, for multiplication, what we are just going to do is multiply the two formulas together. So FG. Well, we're just multiplying the formulas together and we want there to be an x, then we want to say that this x pertains to the combination formula that we get by multiplying them. And so we would write it like this. And then what we would have here, x squared minus x times 3 minus x squared. And then, okay, so this is, again, f of x and g of x. Okay, then you just have to FOIL it all out. So first with first, it's going to be 3x squared. First with second is going to be minus x squared times x squared, which is going to be x to the fourth. Middle ones are going to be minus 3x, and then sorry, second with first is going to be plus x to the third. And if we write this now, so there are no like terms to combine, but if we write it from highest power to lowest, which is the usual standard when there are so many terms, we'll have negative x to the fourth plus x to the third plus 3x squared minus 3x. And here, once again, no forbidden values. So what that means is that the domain is going to be, again, everything. Negative infinity to infinity. Alright, and now the last one, and the one that's going to finally give us something to work with on the domain. We're going to have, finally now, f divided by g. So f divided by g means that if we are going to want to evaluate this at any particular x, what we have to do is take f of x divided by g of x. So this is going to be now x squared minus x. That's the formula for f of x. And g of x is going to be 3 minus x squared. Now, we would simplify this if we could, but what that would mean is if there were any factors that the top and bottom shared that we could cancel. However, we can see that the factors at the top would involve just pulling out a common factor of x, and then that would leave behind x minus 1. And we can see that neither of those is a factor common to the bottom. And in fact, the bottom can't even really be factored in the usual way. So we don't actually have to do much in the way of simplifying here. There's nothing more we really can do. We can just look at this. However, as far as the domain is concerned, we now are dividing by something, so we now have to worry about something. So 3 minus x squared should not equal 0. And what that means then is that 3 should not equal x squared. And then that means if we take the square root of both sides, that x should not equal either positive or negative square root of 3. So that's going to be the domain. So we need negative square root of 3 positive square root of 3 to be excluded. Now, if we want to put this domain in interval notation, we're going to have to take out those two values, so the way that would look is like this. So the domain is going to be everything below negative square root of 3. So that's negative infinity to negative square root of 3. And then it's going to be everything between negative root 3 and positive root 3. And then it's going to be everything from root 3 up. But not including any of those end values. So the whole point of this is that it can't be negative root 3, can't be positive root 3. So it can be everything either before, between, or after those values. Okay, so that's the first case of these, and now let's try something like this. So let's try B, another pair of functions, and this time it's going to be something like this. F of x is equal to 3x squared minus 6x, and g of x is going to equal 1 over 3x. Okay, so let's go through this again with these new functions. Alright, so first we want to add them. F plus g. Now here, once again, the way we write it is f plus g, all of x, and the way we actually do it is we take the pieces and we just put them together. Take the formula for the first one, the formula for the second one, and add them. To add the functions, you just add the formulas. And here, I put parentheses there just to be extra cautious about it, but they're not really actually accomplishing anything, so I'll just take them off. Now here, if we look at this, so we haven't actually really done any simplification, we just rewrote it without the parentheses. If you look at this, there are now forbidden values. Namely, x can't equal 0 here. If x equals 0, then we're going to have 3x equals 0, which means 0 is in the denominator. So that's going to be our domain issue. We can have everything before 0, we can have everything after 0, but we can't have 0. And there's no other amount of simplification we can really do here. We can't do anything because there are no like terms. We can't there's nothing much to do besides this. So we've got everything before 0, so that's negative infinity to 0, not including. And then everything after 0, so that's 0 to infinity, again, not including. And it's going to be very similar for f minus g. There's f minus g. So for f minus g, we are going to go through the same business, and it's going to be f minus g of x is going to equal, well, you take the formula for f of x, you take the formula for g of x, and you just subtract them. So it's going to be a 3x squared minus 6x minus 1 over 3x. And again, it's going to look very similar. And x cannot equal 0. Which means we're going to have the same domain as before. It's going to be negative infinity to 0, not including, and then from 0 to infinity, again, not including. Alright, now here's where things are about to get a little crazy. So fg, so when we multiply these together, we're going to have fg as a function now of x. So we're going to take the two formulas, f of x and g of x, and we're just going to multiply them together. So 3x squared minus 6x times 1 over 3x. Now, the way that we can rearrange this whenever we're multiplying together a fraction like this by something that is not written as a fraction is to rewrite it with this part in the denominator and then see what we can do. So we rewrite this, so f g of x is equal to 3x squared minus 6x, all divided by 3x. And here, if there's any simplification we wish to do, we have to be able to factor and something that is shared by the top and bottom out and then cancel those. But before we do that, let's make a note here. X, it should not be allowed to equal 0 at this stage. Okay. Now this is going to be the same as, if we look at the top, we have a factor that's shared by the two terms, and that's 3x. So if we take 3x out of the first term, all that's going to be left is just an x. And if we take 3x out of the second term, all that's going to be left is just a 2. And then we have a 3x in the bottom, and now those cancel each other, and this is equal to x minus 2. However, if you look at what these functions were to start with, they were two different functions that got multiplied together. And if I had tried to plug 0 into g, that would have been forbidden. Similarly, at this stage of writing it, it would have been forbidden. So even though looking at this you can't see any sign of it, it is still actually the case. Oops, fg of x. Yeah. Jeez, can't help it. My hand just keeps wanting to write f of x. Okay. Fg of x. Fg of x. So fg of x equals that. And then the domain here is still negative infinity to 0, and then 0 to infinity, because it was undefined at that point of simplification. Now we divide them, and so what we're going to get is this: f over g of x. So this is going to be equal to f of x, which is 3x squared minus 6x, divided by all of g, which is 1 over 3x. Now, when you are dividing by a fraction, there are a couple ways you can go about this. One way, one of the most popular ways, is to rewrite this as a multiplication by the reciprocal. When there's only one term, you can do this. So, because there's only one term, We can rewrite this as multiplication by the reciprocal, and that would be fine. An alternative approach would be multiply the entire top by 3x, the entire bottom by 3x, so it would cancel out the bottom. It's your choice which way you want to go about this. I am going to actually go with the second option that I said, so I'm going to multiply top and bottom by 3x, by the common denominator that is shared of the miniature fractions here. And the reason why I'm doing that, you'll see, is as follows. So that way that'll cancel, and there we'll have that. Now notice one thing at this stage, x should not equal 0. Gotta check it at every stage of the simplification, including right here. So x should not equal 0 right there. And this is gonna cancel, that's gonna with that one. And so what we're gonna have is this, which we can distribute to that. And we're gonna have 9x, so x cubed, and then minus 18, an x and an x for an x squared, all divided by 1, or in other words, just 9x cubed minus 18 x squared. Divided by the 1, we can omit that. And here, once again, because of the domain issue at actually an earlier stage of the simplification, not where we ended up, but where we started, we still have to be careful to forbid the value of 0. And the reason, again, is what this technically represents is the formula for f divided by the formula for g, which means that if g happens to be undefined at something like x equals 0, then so will the composition be, or the combination, I should say. Okay, so there's an example, there are a couple examples actually, of the combinations that you can make of the functions, and then also the domain issues that can give rise to. Now, the other way that functions can be combined is by what is called composition. And the idea here is that the output of one function becomes the input of another. So for example, if we have an x here, and we have a function, let's say it is called g of x, then here we can have another function which takes that and in turn eats it. So this is what's going on here. You have an input, and one function swallows the input, produces, and it becomes the output. And then a second function comes and eats that. So the notation here, is we would write f of g of x, or there's another way of writing it, which is f, and then composed with, it's slightly smaller than an O, but it's bigger than a dot. It's like it's a small circle. And we write it like that, and we would say f composed with g. Okay, so there's that, and then the meaning here, g is the inside, f is the outside, so this is the input of f. So the output of g becomes the input of f. And so here this is called the inside. And this is called the outside function. Now let's actually start with an application, just so you can see what this is all about. And one sort of application here would be, suppose that radius is given by r of t is equal to, let's say, something like 3 plus t, where radius is centimeters and t is time in seconds. Then a of r, which is equal to pi r squared, a famous formula, let's say that this gives the area of a circle of radius r. So then the composition of these two functions we would get by taking the one formula and putting it inside the other. Now, which one would make sense? So the composition let's think about what would make sense. R of A, actually, I'll write it in the other notation just so it's easier to see. R of A or A of R. Well, let's think about what's going on here. So the R is giving you the radius as a function of the time. So the input is time, the output is radius. The area is giving you, so A is giving you the area as a function of the radius. So the input is the radius and the output is time. So this one doesn't make sense. This one is nonsense. But this one does make sense. This gives area now as a function of time. So A composed with R of t, this is time in seconds, and this gives area in, it's not just centimeters anymore because it's an area, it's centimeters squared. And actually the formula here is going to be exactly what you think. It's going to be pi times r squared, and the r here is going to be 3 plus t. And we'll just leave it like that. We won't bother simplifying it at all. Okay, so now evaluating compositions. at numbers. So this is going to be the first task, and we'll look at it from a few different perspectives. 1, formula. 2, graphs. 3, tables. And this is where we are going to be plugging in numbers for the x, and we're going to be trying to get the value of the composition. So do this in 2 steps. So evaluate. The inside function, and then plug the result into the outside function. As an example, let's say we wanted to evaluate f of g of 3. And then in each of these examples, we'll have different things for f and g. So first off, let's take as our f. Let's take this to be square root of x. For our g of x, let's take that to be equal to x plus 6. Now let's try to think about what it would mean. F composed with g evaluated at 3. Well, the inside function here is the one that's closest to the number, and that's the g. So step 1 here is going to be to evaluate the inside function, and then step 2 is going to be to take the result of that and put that into the outside function. So, step 1, g of 3. Well, it's going to be 3 plus 6, which equals 9. Step 2 is going to be f of that. Oops, just right. F of g of 3, which is equal to f of 9, as we just said. And then that means take 9 and put that into the formula for f. So it's going to be square root of 9, which equals 3. By the way, it's not plus minus 3 here. If you're just taking the square root, that's only going to be the positive thing. It's if you're trying to solve an equation by doing a square root of a square, but you end up with the plus minus issue. This does not have a plus minus. Okay, so there's that. Now b, we're going to take a different style of functions for our f and our g. So let's say that in b, f of x is the graph that goes like this. And in particular, let's say that 5 here corresponds with the output of, let's say this is equal to 4. Okay. And g of x, let's say, is some graph that goes like so. And importantly here, let's say that 3 here corresponds with a 5 up here. Okay, so I have not given you a whole lot of function values of these two graphs, so hopefully the ones I gave you will be enough to answer the question that we are asking, which is again, f composed with g of 3. So the first question is, what is g of 3? Well, here, what we have is an input of 3 going with an output of 5. And then that means that f of g of 3 will be the same as f of 5. But what output goes with a 5 on the graph of f? That would be a 4. So you just do this in a two-step process. First, you evaluate the inside function. Then you take the result and you put that into the outside function. And then the last format for doing this would be, C, which is going to be a table. And the way the tables are going to look in this section is like this. We're going to have x, f of x, and g of x. Now let's say that our x values in this particular case are going to be 0, 1, 2, 3. Let's say that our f of x's are going to equal, let's say, 0, 1, 4, and 9. So you can see what's going on there. They're each getting squared from the x values. And now, ignore those f values for the time being, and let's say the g values are going to equal -2, -1, 0, and 1. Okay, so we have now our values for the g. Alright, now the way to read a function like this off of a table like this is basically to ignore the other function and just think of it as being a table for g and a table for f, and then to save space they're just put together in one table. So first off, we are still looking for g of 3, and so that's where we start by looking at that one, and that's equal to 1. And then the question is, what is f of g of 3? Which, as we just said, is the same as f of 1. Well, f of 1, that is equal to 1. So this was, so I should write actually in the conclusion of each of these, f composed with g evaluated at 3 is equal to that. F composed with g evaluated at 3 is equal to that. And the same thing is true here as well. F composed with g evaluated at 3 is equal to that. Okay, so that's the 3 ways we can have to evaluate compositions of functions at specific numbers. But that's not the only thing we'll have to do. We'll also have to do such things as find the actual formulas for compositions of functions, which is not in itself usually a very hard process, but we also have to find the domain of the formulas of compositions. Formulas of compositions. Alright, so for the formulas of compositions of functions, what we do is you basically just take the whole formula for the inside function and you put that in place of x in the outside function. Put the whole formula for inside function into the x spot of the outside function. All right, so then here's the issue. We also have to, and then simplify. And then we also have to worry about the domain. So for the domain of a composition of functions, basically it's very similar to what we did with the combinations of functions, in that we are going to find the domain at each specific value, or at each specific stage of the calculation. So find forbidden values at each stage of the calculation, or sorry, of the simplification. And then account for all of these. In the overall domain. All right, so let's now try some things. So first off, let's say find and simplify f of g of x and g of f of x. We won't worry about the domain first. We'll work our way up. All right, and to start with, let's go with something like f of x equals x squared plus 2, and g of x equals the square root of x plus 1. So now let's look at the two things that we're supposed to find here. One is f of g of x, and the other is g of f of x. So f of g of x. So what that's saying is, we take the formula for f, and instead of where there was originally an x, we put the formula for g. So the whole outer part here, is just the original formula for f, just with a big set of parentheses for where the input should go. And here, this is going to be g of x. So there we have that. And then we would do the simplification that we have to do. Now, prior to doing any simplification, you watch out for the forbidden values that would get in the way of the domain. And in particular, x plus 1 has to be greater than or equal to 0, otherwise the square root is not going to be defined. And that in turn means that x, so we can just solve this, is going to be greater than or equal to negative 1. We subtract 1 from both sides. So that's just a sort of side note here. And then that's going to give us x plus 1, because the square root and the square are going to cancel each other out, plus the 2, and we can combine the like terms, and that's going to give us x plus 3. And it doesn't say we have to worry about the domain, but who can help it? we know that x has to be greater than or equal to -1. So that means it's going to be -1 to infinity, including the -1, but not the infinity. So that's the first side of this task. That's finding and simplifying the f of g of x. But then we have to also turn it around and find the g of f of x. So g of f of x so that now is a matter of taking the formula for g, and where there used to be an x, that's where we are going to delicately put the formula for f. So now in here we are going to put the x squared plus 2, which is the formula for f of x. And we would do whatever simplification we could here. Now those parentheses, I put them there to help me organize it, but they're not actually really accomplishing anything. So the 2 and the 1 are like terms, and they can be combined. And so we have that. Now, it didn't ask us for the domain of this, but there's no harm in discussing it. And the thing about the domain of a square root is that you can't have a non-negative value in here. However, squared numbers are always non-negative, and then you add 3, and this is always going to be at least 3. Which means the square root is safe from negative values. Which means then that the domain here is everything. Negative infinity to infinity. Now you may be thinking here, and maybe you accidentally already even did it, that maybe this square root and this square should cancel each other out. But be careful, that only works if this is the square of the whole inside. It has to be the square root of a square. It would have to be blah 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 in parentheses all squared in order for them to cancel out, which it isn't. Okay. Now let's try something else, and let's go with a case of functions like this. F of x is equal to 1 over x plus 1, and g of x is equal to, let's take 2 over x minus 3. Alright, now what we have here when we do the composition is f of g of x, which means where we take the formula for f, and everywhere where there was an x, there will now be this. So it's going to be 2 over x minus 3. Now, this then can be dealt with. This then can be dealt with by taking 1 over 2 over x minus 2, because these are again going to be like terms that can be combined. And when we have an expression like this, then we can actually simplify it by taking the denominator here, the x, and multiplying the entire top and the entire bottom by that in order to clear it out. But before we do that, we should take stock of the domain issues that we can see here, and in particular, there is a domain issue that appears with x were to equal 0. And so then what we're going to have here on the top is just an x, and what we're going to have on the bottom is going to be just a 2, and then we distribute, and it's going to be now, oops, and then it's going to be 2x. So the point of doing this is to cancel the x from the bottom of this. Oops, sorry, you couldn't see that. What happened was I was saying x times the 1, and then x times the 2 over x, so the x's will cancel, and then x times the 2, and that'll make 2x. Now, then here, at this point, actually, so we can't do any more in the way of simplification, but we can ask ourselves about the domain at this point, and we've got a new denominator that can't equal 0. So 2 can't equal 2, or 2 minus 2x can't equal 0, which means that 2 can't equal 2x, which if we divide by 2, we get that x can't equal 1. So that's a new domain issue. X can't equal 1, and x can't equal 0. X not equal to 0, x is not equal to 1. So then if we think about this, we want to put it in interval notation, which is our default notation typically on these. We're talking about everything below 0, between 0 and 1, and after 1. So that's going to be, if we do negative infinity to 0, union, 0 to 1, union, 1 to infinity. And that's only half of it. Then the other half is if we do the g of f of x. So the other half is to go g of f of x, which again is a matter of taking the formula for g, and wherever there used to be an x, now we'll put the formula for f of x. And so here we have 2 divided by, and now it's going to be 1 over x plus 1. Now, right here, looking at this, we want to be careful in that we can't let this denominator as is equal 0. So x plus 1 should not be allowed to equal 0, meaning that x should not be allowed to equal negative 1. Subtract 1 from both sides. Now, if I want to simplify this right here, the easiest way of doing that is to multiply, so ignore that, so the minus 3 is not really relevant yet. Multiply the entire top and the entire bottom of this fraction by x plus 1. And the reason to do that is it'll cancel out the denominator. And then what we're going to have is 2 times x plus 1, or in other words 2x plus 2, all divided by 1 minus 3. And then this is going to give us now just 2x plus 2 minus 3, which is going to be just 2x minus 1. And again, the domain here is that x is not supposed to equal negative 1, which means we've got everything from negative infinity up to just before negative 1, so negative 1 not included, and then everything from negative 1 to infinity, again, not included. So that's how we can do that. Right, now let's see. And now let's look at a couple of special situations that can happen. So, special compositions. So we can have three-step compositions. Three-step compositions such as this. Example, let's say we have f of x equals x minus 3, g of x equals the square root of x plus 1, and then let's say that h of x is equal to x squared minus 1. Then f composed with g composed with h of x would be first on the outside we'd have blank minus 3, and on the inside what we'd have is square root of blank plus 1, and then deep inside that what we'd have is x squared minus 1. So the layers here, we have h of x, we have that inside g, and we have that inside f. So we take h of x, we put that in for the input of g, and then we take that and we put that in for the input of f. So the three layers here are, the outer layer is f, inside that we have g, and inside that, where there's an x, we put x squared minus 1. And then we can simplify this, and for example right here, that 1 and that 1 will cancel, and we're going to have square root of x squared minus 1 plus 1. I'll just first take off those unnecessary parentheses. And so those are going to cancel each other. And then that means we have square root of x squared minus 3. Now here, these, as you're probably suspecting, do some canceling, but they don't cancel exactly quite right. And the reason is because x squared, when you cancel that with an x, when you cancel that, sorry, with the cube root, with the square root, this is going to make everything positive, and the square root will keep it positive. So this is only going to give you the positive version of the result. So that means it's going to be the absolute value. So that's what the three-step composition would be like. You take the formula for h of x. You put that in as the x for g of x. And then you take that and you put that in as the x in f of x. So like the steps here, if we wanted to think of it, was h of x is equal to x squared minus 1, g of h of x in turn would be the square root of that, x squared minus 1 plus 1, and then f of that would be this all minus 3. Sorry, got off screen again. So this would be one of the forms of a special composition. Okay, then the other kind of special composition that we might have is a function composed with itself. So another special composition, f composed with f, or g composed with g. As an example here, let's say f of x is equal to 3x minus 2, and we wanted to find f composed with f So step A, say we want to find f composed with f at a value like 2. And then secondly, we could just want to find the actual formula for f composed with f as a function of x. All right. Well, here what we do is the same as what we would do if it was f of g of x. Just the inside function and the outside function are in this case the same function. So you would just start by saying, well, first, what's f of 2? Well, that's 3 times 2 minus 2. So in other words, it's going to be 6 minus 2, which is in other words 4. All right. And now we say, what is f of 2? Well, we already figured out that the inner part of this evaluates out to make 4. So then it's just a question of what is f of 4? Well, that's going to be 3 times 4 minus 2, which is going to be 12 minus 2, or in other words, 10. And then on the other side, if we just want the formula here, then what we would be doing is we'd be taking the formula for f, which is this, and where we used to have an x, we will instead put the inside function, which is just going to be another copy of f of x. So then we just simplify this all out, and we'll have 9x minus 6 minus 2, which is going to be 9x minus 8. All right. So that is what it looks like when we evaluate a composition of a function with itself. And that's that. So I'll see you next time for the next episode of Math 111. Bye.